Hi, everybody. This is Megan standing in for the usuals. And it's my pleasure to introduce Julieth Saavedra from the Universidad de Ceará, speaking about Laplacian coflow of G2 structures, review, and open questions.
Thank you so much for the invitation. I am happy to be here to introduce my research about geometry people and maybe put more interesting in this area. So I decided to divide my presentation in in 5 steps. One of them is introduce about G2 structure, the theory related to this area. The another is more related to the Laplacian coflow of G2 structure, people working in to know about solution of the Laplacian coflow and some open question that even right now is not solved. And after my job, my paper with Jason and Enrique was on the Laplacian coflow on contact Calabi-Yau manifold. But in this paper, you can find another flow, is the Laplacian flow and the heat chain flow. But right now, I am interested more in talk about Laplacian coflow. And also the paper working with Andres Moreno, a PhD, a postdoc student in the Campinas University, Brazil. We are working about the Laplacian coflow, but just in almost Abelian Lie groups, taking some ideas given by Jorge Lauret. So, okay, to talk about G2 structure, the first thing that I need to introduce is about octonions, because the G2 structure has a connection between octonions with G2 structure. Why? Because the octonions is an 8-dimensional real normed division algebra, but we have there algebra over R with multiplicative identity 1 different to 0, such that satisfies this equality respect to the norm, when the norm, where the norm is given by the usual norm on the real R8, and the metric is the usual metric. So this part is related to a real norm division algebra. It's not necessary to be 8, it's just the definition about real norm of norm division algebra. This, in fact, there are only 3 cases about this real norm division algebra. Is the complex number, the quaternions, and octonions. But for me, I am more interested in to talk about octonions. So using the Euclidean norm, we can divide this space, the vectorial space, into subspace. One of them is given by the real part of the octonions that is generated by the identity. And the another is the orthogonal part of the real part of the octonions, this R7, that we usually take this isomorphisms with the imaginary part. So right now, working in the normed division algebra, the second thing to be useful is that note that this algebra is not commutative and associative. So we can define the bilinear map on the octonions that is given by this Lie bracket. A taking 2 elements of the octonions, A and B, we can define the commutator, AB equal to A times B minus B times A, where this product is given by the octonion that we usually know. More even, we can define the associator that is a trilinear map on the octonions, which is given by the last equation. We take 3 elements of the octonions, and we first take the product on 2 elements A, B, and after product C minus A by for the product on B, C. So, right now I am trying to introduce you the algebraic structure in the imaginary part of the octonion. So For more information about this part, I guess an interesting book, an interesting paper is given by Harvey and Lawson about calibrate structures. They put any equation useful in norm algebra, norm division algebra norm. But for me, in the imaginary part of the octonions, used the commutator and associator, we can define the tree form and the associative tree form and co-associative form given by phi. I am so sorry. This part is not phi, it's psi. Usually, we define by psi the co-associative form. So here is a mistake mine. And more even, just taking the imaginary part of the octonions, we can define the vector cross product on imaginary part of the octonions. Some question? No, okay. So we can define the cross product, the vector cross product on the imaginary part of the octonions, which is defined by the imaginary part of the product given by the octonions. So this defines the associative tree form, just taking the vector cross product. And right now, we can define what is the group that belong to GLR, which stabilize this tree form. The group that stabilizes this tree form is G2, but this G2 has important properties, which is compact and is simply connected and is contained in SO7. So using that, give me some minutes just to, okay. So right now, what is the second thing that I would like to talk about this G2 structure is to generalize, not to take only R7, the imaginary part of the octonions, is to take a manifold which the tangent bundle is the manifold 7-dimensional. So we know that in any point the tangent bundle is isomorphic to R7. So the second thing is when this manifold admit a cross product. In fact, it's not if I take a 7 manifold, it's not necessary to have a cross product, need to be a spin and orientable manifold to admit a G2 structure. So after that, we know that the manifold is a spin and orientable, we can define a bundle, a positive tree forms, which is given by using the shared coordinates and the homomorphisms given by these shared coordinates with R7. Push forward the phi. Here I put it this phi, but it's the same phi defined in the last picture. So we take this this associative tree form in R7, and after we define this in the tangent bundle. This section of this section. Any section of this positive tree form give us an G2 structure. But this G2 structure we give us also the associative metric given by the last question. So right now, after to take this bundle and the G2 structure, we will take the metric, the associate metric. So the next step is to ask about anything related to Riemannian manifolds. So for this, we need to introduce more tensors that could be useful in the analyzing the Ricci and the curvature in any manifold that admits a G2 structure. So using the associated metric, we can define the dual form, but not that this psi is the connection. We have this connection with the co-associative form. So, and in fact, the stabilizer of this form is also G2 times Z2. So we have C2. So we have, in that case, the psi, we give us a 2G2 structure with different orientation. Using the G2 representation, we decompose the space of the differential forms for, in the case of omega 2, for the two subspace given by this equation, this relation, and the three forms given by these relations. Using the last one, using the map such that take any symmetric tensor and give us a three form, and this S02 is the trussless symmetric matrix. So right now we have the decomposition on the differential forms, but for the another case, using the property that we are working in seven-dimensional manifolds. So for the case to omega 4 and omega 5 is just to use the Hodge properties, but it's the same. The four forms is we have the division of one space, the dimension 1 generated by C, another with 7 and another 27, but here the change is the four forms using the Hodge operator, and the similar case in the the 5 forms. One of the most common examples working with G2 structure is related to Calabi-Yau manifolds and nearly Kähler manifolds. Of course, also we have some examples on homogeneous space that maybe in the next talk or after I will give if I have time, maybe. So, but here in these three examples, it's more easy to know the way that I would like to go, because if I start, for example, with a Calabi-Yau two-fold, we know that in the case to be a Calabi-Yau two-folds, we have a Kähler form, and we have a metric and the almost complex structure that is compatible with this metric. So this Kähler form. So using that in the product manifolds, there are 3 times M or T3, where T3 is S1, is the torus, the flat torus. S1 times S1, what times S1. And using the metric given by the product, we can define the tree form, and this tree form is a positive tree form and give us a cross product on the tangent bundle. And more even, the Hodge operator is given by this 4 form. Note that if we apply the phi, the phi will be equal to 0, and the psi will be equal to 0. So it's just an example. The same case we can do in the case to Calabi-Yau threefold using the Kähler form, and but in that case will be times S1 or S or R, and the metric is given by the x, where x is the coordinates given by R or S1. And we can define the tree form given by this using the three-zero holomorphic form in the case to be a Calabi-Yau. And the Hodge operator of this tree form will be this 4 form. The same than the another, the phi it's equal to 0 and the psi it's equal to 0. In this, the another example is a little different, because even if I take a Kähler, a nearly Kähler manifold, but which is the omega equal to -3 real part of epsilon, with this epsilon satisfies this relation to be a SU3 structure with omega. We have this trip epsilon, omega, and G that have the relation that omega to omega wedge, omega, it's equal to some number 8i, I believe. I'm not sure right now. Omega wedge conjugate to omega. This is the relation to be an SU3 structure. So using the Nearly-Kähler manifold, we can define also a tree form. We not will be the x which omega plus real part of epsilon, but not that the phi it's not zero. It's another kind of G2 structure, but it's not closed. What is closed? I will define this kind of G2 structures. So some approach of G2 structure is more used forms. So it's interesting to know what is going on in the cohomology class. For that, we need to know, we define the torsion forms. This torsion forms is equal to, the phi is equal to tau 0 psi plus 3 tau 1 wedge phi plus Hodge operator of this tau 3, using the decomposition of the 4 forms. The similar idea in the 5 forms, we have one tensor tau 1 and one form tau 1 and two form tau 2, which define deep psi. And we say that this tau 0, tau 1, tau 2, and tau 3 will be the torsion forms of this G2 structure. And so we have, right now I will give some classes of G2 structure. One of the more important class is this of to be torsion-free. So to be torsion-free is using the metric, the associated metric. We can define the Levi-Civita connection, and the Levi-Civita connection we find it's equal to 0. This is to be a torsion-free. But Fernandez and Gray show that this condition implied to be closed, which is the phi equal to 0, and co-closed, that is the psi equal to 0. Another kind of G2 structure useful also is nearly parallel the phi, which is the phi equal to C psi. So this is some classes of G2 structure that will be useful to say, because I will work with co-closed G2 structure, and in fact, then to be nearly parallel implied to be also a co-closed condition. So full torsion tensor give us an idea about the geometry, the Riemannian geometry of this 7 manifold. And this full torsion tensor is a tensor that is connected with the forms, the torsion forms. So we have here the tensor defined by the equation 1, and after using only the case to be co-closed, we have that the Ricci is equal to minus the rotational, though this the rotational is given by this formula, minus t to 2 plus trace of t. So here the full torsion, knowing the full torsion tensor, we will know about what is the Ricci tensor and the scalar curvature on the manifold. So using this approach, I would like to talk about the people working on Laplacian coflow of G2 structure. Why Laplacian coflow? The Laplacian flow, the Laplacian flow was working by Brian and Sue, and he showed that this Laplacian flow is given by the functional volume, and more even the gradient of this, the critical points of the gradient of this functional will give us a torsion, G2 structure torsion free. So using this approach, Karagiannis, McHugh, and Su introduce the Laplacian coflow, but in that case, they study only using the product manifold, giving the examples to be nearly Kähler and to be Calabi-Yau, and using the flow, analyzing the soliton solution of this flow. But after Brian showed that the Laplacian flow, not the coflow, the Laplacian flow, that it's similar. Difference is that they have here the phi and phi. In my case, it's psi, and the initial value is close. In our case, is co-close. So Brian and Su show that the Laplacian flow that exists, and more even is unique. The solution is uniqueness. Using this approach, Grigorian tried to use the torsion to define this, to understand better if this flow is there are a uniqueness, and solution, and uniqueness solution. But the problem is related to the divergence. So he needs to put a new term to show the uniqueness and existence, but this flow is totally different of the Laplacian coflow. There are connections, but it's not, they not imply that the Laplacian coflow exists and is uniqueness. So using this, we have the modified Laplacian coflow. For this modified Laplacian coflow, we know uniqueness, existence, and some approach given by Shen about cannon-collapsing theorem using techniques given by Lotte and Wei in chi-types estimatives from the Laplacian flow. Grigorian also study in the case soliton solutions, in the case to be a Laplace, to be a nearly Kähler and Calabi-Yau on the product manifolds. So after they use the approach to be Calabi-Yau and nearly Kähler, and so approach given by Brian, but Pagaglini and Fini study the explicit immortal solutions of the Laplacian coflow on subclasses of almost Abelian Lie groups, and more even, Bagaglani and Fernandez and Fino obtain explicit immortal solution of the Laplacian coflow when M is the 7-dimensional Heisenberg group. Lotte, Serb, and me prove that existence of the family of Jitter structures solving in a specific case on contact Calabi-Yau structures, that I will define what is it in the next step. And more recently, Lotte and Keno use the Laplacian coflow, but on 3 Sasakian manifolds, and they show some stability or not in the nearly parallel G2 structures, because the nearly parallel is the auto reforms on the Laplacian. So this is the several authors working in the Laplacian coflow. Right now, the second thing is, what is the Laplacian coflow? The Laplacian coflow is taking a tree-form G2 structure 5,0. We obtain the 4-form psi, and of this psi, we will deform in the direction of the Laplacian coflow with the initial value depth psi equal to 0. That is to be a co-close. And Karagiannis showed that the volume, if M is a compact manifold, the Laplacian coflow is the gradient flow of the volume functional, and psi define a torsion-free G2 structure if and only if it's a critical point of the functional V restricted to the cohomology class psi. And this is a work with Andres Moreno. So all of the authors was working in a specific case. We are more interested in analyze what is the Lie derivative of the any vector field giving a G2 structure 5. So the Laplacian soliton for coflows G2 structure is satisfying this condition using the approach to be co-close. And the theorem important given by in the paper with Andres is we decompose the Lie derivative psi in in any case, and using the decompose given by Gregorian, this decomposition was given by Gregorian. We conclude that to be a soliton solution, it's necessary to satisfy both equations. The equation number 7, the divergence of the full tensor equal to -1/2 rotational of the vector field, plus the contraction, the vector field contracted to the full torsion tensor, and the next that is more related to the Rishi, and here we have, if we put more conditions, we would like to understand better about solitons on the Rishi flow using in the Laplacian coflow. But this is our next work. So this is related to a soliton solution. Right now, I am give the importance things about Laplacian coflow on contact Calabi-Yau manifolds. What is to be contact? To be contact, we have one form on R2n+1, satisfying this equation, which is eta wage d eta n, it's different to 0. So the contact form give us some relation with the volume form. What is about the contact manifold? The contact manifold is a 2n+1 dimensional manifold that admits and contact one form, a contact one form. If I have almost contact structure, we have the manifold 2n+1 dimensional, a one form, and vector field, and one endomorphisms that anyone connect with these relations. This is to be almost contact structure. And if I have more Riemannian metric on this manifold, we will say that this metric is compatible with these endomorphisms. It satisfies the equation 10. Using that, on almost contact structure, we can define the two forms given by the metric with the connection with this metric and the endomorphisms 1, 1. And the volume is the volume of this manifold will give given by the equation number 12. So what is about to be contact Calabi-Yau manifold is to be a Sassakian manifold, which is there exists a triplet satisfying to be almost contact structure, and the cone is a Kähler manifold. And more even, we have in the distribution is this D that is equal to the kernel of eta, satisfying this condition. Or looking in another way, is a Sassakian manifold with admit a 304 and holomorphic 304. This is to be contact Calabi-Yau manifold. Using that, Habib and Bessoni show that if I have a contact Calabi-Yau manifold, there exists a co-calibrated structure defined by eta wage omega plus real part epsilon. So we use this. Oh my God. Okay. We use this to consider another family of G2 structure depending of the time given by the equation 14, which the initial date, initial value is given by 13. So this family will have the initial value to be co-close. And after we put in the coflow and we conclude that this family is a solution of this G2 structure. The solution of the Laplacian coflow will be given by the equation, the third form given by 16, and the fourth form will be given by 17. Note that this three form we have the polynomial minus 1, so there exists a singularity of this flow, of this solution given in the Laplacian coflow. The metric is given by pt 2 minus 6 era 0 2 plus pt 2, the metric in the distribution, and the volume form is given by this polynomial pt 2 3, the volume form of the initial manifold. And if we put t going in the time to infinitive, the volume grow up also, but not that the metric is different, because if we put t going in infinitive, the circle given by era 0 will be less, will be a little. Some question? Will be a little, and the metric is like to lose in the time this one dimension, and to be just to take 7 dimension, and in the time just going something to Calabi-Yau, to be a Calabi-Yau manifold. The remaining curvature is a polynomial 2 minus 2 over 5 times the remaining curvature of the initial manifold plus a polynomial depending on the time. And this is the second step. Say that if I take time, the time going in infinitive, we have the volume going to infinitive. And the relation for any metric is, if I take in the interval minus 1 over 10 epsilon 2 to infinitive, this is uniformly continuous, a family of uniformly continuous, but taking in another in minus 1 over 10 2 like times t or t infinitive, this is not necessary to uniformly continuous. Right now, the full tensor torsion is given by this part. Why I need to find the full torsion tensor? Because the full torsion tensor help us to analyze the singularity and to define what kind of the singularity we are obtaining. For this, we use the Shen paper, that the Shen paper give a Shen dilatons of the Ricci-like flow, using the norm of the curvature, the norm of the full torsion tensor, and the norm of the connection with this full torsion tensor. So using this in our family, we can find the norm, the nabla of this full torsion tensor, and more even, just to be clear, what is the divergence, because this is the principal problem of the Laplacian coflow, but in our case it's equal to 0. Here, using the same approach in Ricci flow, that is classify any singularity, we can do the same in the Laplacian coflow, so, or Laplacian flow. So for instance, our solution is the type 2b in some, when t is equal, when the dilaton is going to minus 1 over 10 epsilon, and 3 if the singularity is going to infinity, because we have two singularities. The first is minus 1 over 10 epsilon, and the another is infinitive. So this is the thing that I am saying is giving the proposition. If M is compact, a compact manifold, and K is equal to the sum of the norm, the curvature in the distribution, then the dilaton is given by K2 for 1 plus 10 epsilon 2 T, all of this to minus 2 over 5 plus the polynomial depending of the time. And if we put this, if we analyze what is the sum of T lambda T, or in any case, or sub to T minus T of this dilaton, we show that the first is type 2b and the second is type 3. So this is anything about Laplacian coflow on this specific case. What about the Laplacian coflow on almost abelian Lie groups? Okay. On almost abelian Lie groups, we have what is the almost abelian? Is a Lie group G which admits a codimension 1 abelian ideal H. So using this basis of H, and consider the another element orthogonal of this basis is 7, defining the G2 structure given by omega wedge 7 plus rho plus, when rho plus is the real part of this epsilon that we are knowing using the U3 structure. And the psi is equal to equation 19 in the cardinal coordinates. So this approach is more using the Jorge Lauret's paper that he works on Laplacian. I am not sure. Sorry. Okay. Okay. So we have here the coflows using the Lauret paper. He gives the condition to be close and coclose using the matrix A, where the matrix A is given by I define here. The metric A is given by the adjoint of the represented adjoint of this element S7, restrict to the sub algebra H and the subspace H. Sorry. So using this, Lauret show what is the condition to be close and close. So we are interested in it to be a close. So in that case, we're interested in matrix belong to SP3R. But here in the paper to Lauret is to take a flow on a manifold on a manifold on a Lie group on homogeneous space more specifically, and to analyze not the flow, to analyze more the bracket flow. So for this bracket flow, we input an action of the GL, the space, the GL G, where the action is given by the pullback of the inverse of this matrix. And this action gives us an infinitesimal representation on the positive tree forms, which is given by this theta. Using this theta, they give us that any tree form on the space here, key phi, for any tree form on this space, there exists an operator key pi, key beta, belong to this key phi, such that beta will be equal to theta of this operator, of this unique operator, action with this phi, where phi, the action is given by this, no? The infinitesimal representation. So if I would like to analyze, if I will change this flow, the Laplacian flow to the bracket flow, it's necessary to know about the equivalence. So these two homogeneous spaces are equivalent if there exists an equivariant diffeomorphism F in the homogeneous space. There is F determine a Lie group isomorphisms G, taking K into the K tilde, such that phi is equal to the pull-back of the another phi tilde. This is to be an equivariantly equivalent. On almost Lie group, we will say that equivalent using the metrics given by the adjunct of the element S7 is the relation to exist a Lie algebra isomorphisms H such that the pullback of phi is equal to phi. So we have the family of G2 structures satisfied to be solved, which solve the Laplacian coflow. So for any, we find metrics and linear transformation HT, which just to be an action of the initial, and using that on the Laplacian and the infinitesimal representation, he is just to know what is the behavior about this linear transformation using the key given by any four forms psi. Right now, changing on the another part to use the bracket flow, so we can define for any H a bracket, an action of the initial bracket flow, and the idea is to have this equivalence between the first, the initial Lie group G with the solution of the Laplacian coflow, and the another is just to take the G2 structure, but changing the bracket flow using this isomorphisms H. But what is the Ka in the almost abelian Lie groups? Using the co-close condition. Using the co-close condition is just to Ka is just to satisfy this equality, equality 28. So in particular, we will say that two algebras are isomorphisms. I'm sorry, I am not sure. Okay. Two algebra isomorphisms between GA and the first, the solution to be of this flow, and the another, the solution of the bracket. So the idea was solving this equation 30 for an specifically just to take Ka given by the equation 28 in 29, and after is just to solve the differential ordinary equation given by 13. This equation, we have a solution of the Laplacian coflow if with the initial date 0 exists an equivariant isomorphisms Ft such that this Ht is equal to the differential of this equivariant isomorphisms, solving the last equation. And in addition, the family that is solving the Laplacian coflow is just the the pullback of the initial phi, of where this Ht is the solution of this equation 29. and AT is given by this. So, and specifically, we will define family A that will be a solution, which is given by this equation 31. So what about a specifically example? If we consider the family of the matrix A, which is this matrix A is belong to SP3R, and B in a specific case given by this. So this the equation using the equation 31, the differential ordinary equation is given by 32. And solving this equation, we will have the family given by this picture. So the trajectories of the level curves is given by this. And if we note here, the red line will be an G-nucleant curve of this differential ordinary equation, and the green part will be the X-client, null client of this differential equation that help us to understand what's going on about this flow of this specific case. And more even, the pink is the case where is also a critical point of this differential equation, but this is, pink is in fact is a G2 structure belong to is the case when we have closed and co-closed. So is this a family of G2 structure with torsion-free? What about open problems about the Laplacian coflow? Right now, there are not a paper that show existence and uniqueness on Laplacian flow. This is an open question, open problem right now. And the another open problem is related to the critical points on the the relation, maybe more clear about the modified Laplacian coflow, because the modified Laplacian coflow, we know that there exists a uniqueness and existence, but we would like to know more about the relation between Laplacian coflow and Laplacian flow, and the critical points of the Laplacian coflow, maybe in more general cases. And maybe this Laplacian flow could be useful also maybe in the case to be associative submanifold, but this is another thing. So this is my talk. Thank you so much. I finished. And if you would like to know about the Laplacian coflow of G2 structure, I recommend the paper of Gregorian flow for coflow G2 structure, and more if related to the Ricci-like flows, I recommend is more geometric analysis of flows. I recommend the Shem. And the another is to the modified Laplacian coflow is this of Gregorian. And this is the paper that I would like to say about G2 structure. Thank you so much, and thanks for the invitation. If any question, please let me know.
Well, thank you so much, Juliet, for a very nice talk. Perfectly timed. Yeah. Are there any questions?
No.
Nobody has any questions. Could you go back to your flow, just the image? Yeah, that okay. Could you
Yeah.
all right.
Yeah.
What could you say again what the green and the red lines?
The green lines is x nucleon. So using the differential ordinary equation is when x point is equal to 0, and the another is when its point is equal to 0. It's not a critical point of the system. It's just the vertical vector fields in that equation, in that differential ordinary equation, and the horizontal vectors. But the pink is more the critical points. In fact, the critical points is given by this pink line,
Okay.
which is the elements that it's equal to 0, the critical points.
Thank you.
So my idea here is more after is something that I am working right now, is to analyze these cases more in the way using differential ordinary tools, equation tools. So I am working with the colleagues just to know more about this way in dynamical systems. Yes, it's something that I am trying to understand better.
Yeah. A little bit more low dimensional or something. Yeah. Anyone else have questions? If not, let's I don't even know if I said let's thank you the first time, but
Thank you so much.
second time.
Thank you so much for the invitation. Thank you. I am sorry. I am follow the seminar all time. So thank you.
It's I'm also very happy to have it exist. It's nice to be able to do that.
Thank you very much, Juliet.
Thank you so much.
Megan, maybe you may stop the recording, clicking the red button.
Okay.
That work? Yeah. Okay.
It's okay. Yes.
Yep.
I think it is recording.
Oh, still.